Okay, what's up, everyone? We solved part 1 of this earlier, and thanks everyone for tuning in. Now I'm going to go ahead and solve part 2. So, just to kind of show you guys, for people who just tuned in right now, I have it solving the actual input for part 1 pretty quick, 5 milliseconds, I guess. So that's fast enough, you know. And I did spend 0 time tuning this. You know, I did try to write some of the rules a little bit like with performance in mind, which I guess now is just going to be more work for us to go back and kind of rework them so they work for part 2. So I was reading through part 2, and it sounds like we just want to, there's like no kind of like defined like picture shape or something. It's not like keep iterating, you know, a million times till you get this exact picture. I think it's just kind of step through it one by one until you get a picture. And, you know, so what does the Christmas tree look like? Who knows? But I guess we'll just step through it till we see a Christmas tree. So first thing we need to do, I guess, is come up with some code that will print out where all the robots are. So I think the way I'm going to do this is, if you guys remember from earlier, we have all the robot positions. And actually, yeah, so do we have all the robots? Like, so, okay, so it's like this. So we do, so let's say for like the example input, we have, you know, the example size, and then we have the robots, right? And so these are our robots. And we could say, like, let's look at all the robots in that list. Let's say right line. So for each robot, let's write a line. So these are all of our robots, right? So we can do that. We have that. I think the next step is we need to be able to get the robots for each second. So what we're doing right now is we're moving the robots, and then we're calculating the safety factor size. That's how we're solving part 1. But let's say for part 2, so I guess there's 2 parts. We need to kind of rework this a little bit so we can move robots one step at a time. That's not going to be very hard. The other part is we just need to print out all the robots. And I guess we could just kind of iterate through all the positions and then print them. If there's a robot, you know, we'll print like a X or something, and if there's not, we'll print a dot maybe. I think that's probably good enough for now. We have like, I don't know, like 10 robots. So 11 by 7 is, what is that, 77? So we're going to have to kind of search through the list 77 times, and it's a list of 10. Is that going to be fast enough to print it if we're iterating by hand? I think it's going to be fine. So, you know, we could do something more exotic, like a little tree structure or something, but I think that's going to be too much, you know. So let's just write some code to print our robots out. So we'll call it print robots. And this will just be a rule that always succeeds. You know, it'll look like that. And I guess actually, no, we need to know the size of the board so we can iterate through all the positions. So we'll do that size. And then let's write a rule that gives us all the positions in a bathroom of a given size. So we'll call it position. Okay, so we want this rule to kind of succeed once, to give us, like, spit out all the different positions. So size, we remember from earlier, is actually a list of height. No, did we say width times height? I'm doing it again. I'm already forgetting. Width and height, and then position will be, you know, X, Y. Okay. So this is actually, we could just use finite domain stuff here. We can just say X and 0 to, so we're doing 0-based indexing, so it has to be width minus 1, right? So we'll do max X, max Y is height, minus 1, Y, and 0. Okay, so now we should be able to get all the positions in a room size. So if, oops. So for the example, size is 11 by 7, right? So let's look at all the positions for the example. Oh, we got to use label to give it like a real value. Okay, so right now it's just kind of like a constrained logic variable, but we want to actually tell it solve for all the values of position, you know, so. Position, oh, sorry, I wanted it to be X, Y, I wanted it to be a list, not a pair. There we go. Blah, 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 blah. Okay, cool. So now we got all the positions, okay? So now we just gotta loop through all the positions. Is there a robot at the position? If there is, we'll print something, and if not, there's not. So actually we could kind of break that down a little bit more. Robot at position. Position, okay. And remember from earlier, a robot is just a little dictionary that looks like this, you know, so it has two keys. P is the position and V is the velocity. We don't care about velocity right now though. So let's write a rule. A robot is at a position if a robot is at position XY if it's a robot and its position is XY. Actually, we don't even need to go that far. We can just leave that structured instead of destructuring it. I think that's the whole rule, right? I don't know if we need to tell it it's okay for it to have velocity, right? So let's get one of our robots from earlier. Said, give me a robot. So here's an example robot, and we'll say, is this robot at position 9,5? Oh, it's not? Okay, I do have to do bind velocity. Doesn't matter what velocity is. Yes, okay. And the cool thing about this is, you know, we could like run it backwards, we can say, or maybe not run it backwards, but we can like have it solve for something. What position is the robot at, you know? So actually I'm gonna call this robot position. So let's say robot position. Cool. I guess, you know, we can have it partially. I think we can have it partially solve for robot, maybe. Come on, thing. So yeah, so we could say, give me a robot at position 9,5, and it'll spit out, you know, I guess, not a fully instantiated robot, but a robot whose position is 9,5, and then, you know, velocity can be filled in later. But we're not going to need to run it in that direction, okay? So given our list of robots, now what we want to do is just kind of iterate over each position of the possible positions, and then if there is any robot at that position, and I guess there could be multiple robots at the position, but we just need to know if there's one there. So if there's any robot at the position, then I guess we'll like print an X or something. And if not, we will print a Y. So let's try to get our code to iterate over the positions working. So let's say, we'll call it print robots. And let's say, okay, and we'll write this recursively, I think. So let's see, width, height. Yeah, okay. So the very first iteration, you'll pass in size, and then we'll call it with the one arity right here, right? Robots, and then that will hand off to the two arity, and it's going to start at 0, 0, okay? And then, so we know we're done printing robots when we get to width and height. So, you know, if like it's a 5 by 5 room and we get to 5, 5, then we're done because it's 0 index, right? And then we'll just increment X and Y, or I guess we'll increment X every time until it gets to width, and in which case we'll reset it to 0 and increment Y. Okay, so let's write that rule. Width and height. X is width, then for some Y, then we're going to recurse. We'll say new X equals 0, Y equals Y plus 1, Y plus 1. And then we'll say recurse print robots width, height, new X, new Y. Okay, so we got to do two things though. This rule would also match when Y equals height, you know, but we want this rule to apply instead. So what we're going to say is this rule only applies if Y is less than height. Okay, cool. Okay, and I guess the other thing is new X is not accomplishing much. Let's just take that out of the equation, and we'll just put 0 right there. Yeah, okay, so The other thing, so now this is gonna, every time x gets too big, we're gonna go, jump back. We're gonna jump to the start of the next line, okay? Okay. So now let's print robots. This one will iterate for each value of x. X, y. We'll say x is less than height. Same thing, we don't want this other rule is supposed to be the one that takes care of things, you know, when we get to width and height. So this rule should only apply, and we don't want this other rule for that matter to apply. You know, if x is equal to width, we want this rule to apply and not this other rule. So this rule only applies when x and y are both less than, width and height, okay? Now we'll do something. You know, let's just print x for right now. And I guess every time we get to the end of a line, we should probably print a new line. You could do that with just NL. We'll write a new line. So I think if we do this, it should be like 0, 1, 2, 3, 4, 5, 6, 7, 0, 1, 2, 3, 4, 5, 6, 7, right? So let's try this out. Uh-oh, that's not what it's supposed to do at all, is it? So at this point, I'm like, what the heck did I do wrong? Right, x. Oh, forgot to have it recurse. Okay. Okay. Yeah, okay, cool. So there we go. Now it's printing a board. So I guess the only missing ingredient here is we need to write that code to print a robot, you know, or yeah, print an X if there's a robot or a dot if there's not, instead of printing just the value of X for each X. So I think what we could do here is actually, we'll call this like, why don't we call this like iterate over position or something? You know what? Why did I write this position rule? Man, I'm tripping. We don't need to do any of this stuff with all this code. Too much. Watch this. I'll show you a better way to write it. Let's see. Okay. Actually, we'll do this size. And then we'll say right x, and we'll say if y is, let's see, if y is equal to height minus 1, you know, the end, so x is equal to width minus 1, you know, the end of the line, then we'll write a new line. Otherwise, yeah, we don't want this to backtrack, so we're going to use the pointy arrow operator. It's kind of like an if-else, you know. Otherwise, this can just succeed, okay? And then, yeah, that should do it. And then, you know, we just got to, so this will actually kind of unify, I guess, once for each position. And all we got to do is just have it kind of find all or something like that. Let's try this out. Print. Oops. Hey, what the heck? Oh, sorry. Yeah. Wait a minute. Where was right next? Print robots. Where wasn't it? Oh, geez, what did I just do? Wasn't it not writing anything, huh? For each position, it's supposed to write X. Okay. Then, yeah. Okay, why is this only succeeding one time? Let's try it like that. Oh, you know what? Because we're not getting concrete values, a label of, of the position. There we go. Bam, 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 X. Oh, yeah, okay, so it's doing... Yeah, so it looks like it's going... Are we doing all the X's, all the Y's first? Let's try to print them both out. X, Y, X, Y, X, Y. Right. Okay, so I think it's kind of printing sideways. But the other missing ingredient here is we want it to just find all, you know, so find all. Let's do it like this. Find all position. That's okay, but we gotta move this rule. Find all. That's not how you do it anyways, right? Find every position in the rule print robots. Position, blah, 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 blah. Yeah, okay. So it is printing everything now. Let's put our new line code in there. So we'll call this is the real print robots. I don't even know if we needed to even have it find all or something. You could probably... There's some other way to do this, you know, because right now it's basically unifying, you know, each value position. It's basically creating a list of all the positions that I'm immediately discarding, and there's no point to that, right? So maybe it'd be a little bit more efficient if we just got all the matches of the goal and then just had it do some kind of something for side effects, like print robots that, you know, did not actually have to return the position. But I guess we're splitting hairs here, and it's not super important. It's probably not going to make a difference in terms of solving this. So, width. Okay, so let's see. Oh heck, what the heck did I do? Print robots. Yep. Okay, we don't want to print two things. Okay, so we gotta think. We want to get every value of y and then every value of x. There we go. Okay, cool. That's our new print robots. That's pretty simple, right? Basically, it's just finding every position, solving for values of y first, and then solving for all the values of x. You know, it's basically solving for every possible position, and then finding every position and printing robots, you know, for all those positions, right? So, cool. So now we're just printing x. We need to actually print robots. So let's just say print robot should also take robots as a parameter. This isn't printing robots. This is printing a robot. So I'm going to rename that. Print robots does print them all though. So this takes robots now. Cool. And so I guess the other thing now is we just need to decide how to print it. Okay. So, well, this is the code for printing a new line. So this will be the code for printing robot or not robot. Okay. So we'll say if it's a robot position, okay, let's think about this. A robot is a member of robots. If there's a robot at that position, any robot, we're just looking for one solution here, right? We might be, okay. We might be messing up and printing more than once if there's multiple robots in a position, because I guess find all would... Oh no, we'll do a cut. We'll do a cut. So, okay. Robot position is position. Yeah. So basically, if there's a robot at that position, then okay. Then we will let's group these together. Yeah. Okay. So by putting this cut here, using the arrow, it's cutting, which means, you know, we'll not try to find multiple things that match this goal. So that's probably fine. So we say right Otherwise, we're gonna write a dot. I think that should do it. Let's give that a go. Oh, why are we all X's now, huh? What? Robot position. That can't. Wait a minute. Print robots. Oh, because robots. Yeah, okay. We don't have any actual value of robots, so I guess it's just unifying with something that has no value. And we're saying, well, we're kind of running this backwards and saying, well, you know, there's a robot that's a member of this list. You know, like, well, this list isn't instantiated. Sure, it can unify with a list that has that robot in it. So we need to do this. Okay, so. Yeah, okay, there we go. Now we're printing all our robots. That's cool. So now the only other thing we need to do here is just make this iterate for n number of times. And then we can just have it like continue to spit out answers for different values of n until we're happy, and at which point we'll copy paste our answer into the input and call it a day. So let's write that code. We'll do it like this. Input. Right. This is going to conflict with the other one. Okay. We're going to call it print robots in. Okay. So we're going to say size. Let's get the size for a different input. Like we have the example and the actual input. We'll get the robots. And then we'll say we got to move these robots in times. Okay, so move robots. What do we move? Robots. I'm just going to copy that. Okay. Yeah, we'll call this n moves. Size robots, moved robots. Okay, and then we're going to print robots. Okay, so print robots in for the example and 0 should give us the same thing we just had, right? Yep, okay. And for 1, you know, now they moved, that's cool. So we'll do this. So we'll say n is in, we'll just say it's greater than or equal to 0, okay? And then now we should be able to get multiple answers. So it'll basically give us one answer, and then we'll say give me more, and then it'll backtrack and do the next higher value n. And then, you know, keep solving for, oops. Yeah. What the heck are you talking about? Print robots example. Right. Okay. So anyways, what I was saying a second ago is about what we want to do, but we don't need to like instantiate all this stuff over and over again every single time. Why don't we cut here, and then it can backtrack. We'll say, oh, yeah, n is in the domain. Let's say 0. No. Okay, we'll just say, I think this should be fine. N moves, not. Gotta make sure we use the same name for everything. Okay, so what should be happening is we'll instantiate size based on input and robots based on input. Okay, then we'll cut. It'll eliminate all the choice points before this. Okay, then moves is basically starting at 0, and every time we try to do this goal again, it'll go up by 1. So it'll be 0, then 1, and we're instantiating that as like a real actual concrete value. So we'll have 0, 1, 2, and then we'll move robots, 0 times, print it, move it 1 time. And so I think this should let us kind of iterate through each thing, right? So allegedly, yeah, that's the idea, but it says, what are we doing wrong? Yeah, it doesn't like it because n is unbounded. And you know what, I think you would think that wouldn't matter because it starts at 0 and it should just keep going forever. But it's being fussy. So anyways, yep, now I could keep iterating through it 1 by 1. That's cool. So let's quit that, and we'll use the actual input now. And then hopefully I'm hoping we get this within a reasonable amount of time, because I think this picture we're supposed to be able to recognize it looks like a Christmas tree. It's not something we're supposed to like programmatically solve, I guess. So, well, that doesn't look like a Christmas tree. Neither does that. I don't want to be here all day looking at Christmas trees, right? If it's like more than like a few hundred or something, then I'll give up and think of something else. But oh, was that a tree? What the heck was that? Something, huh? Not a tree though. Wow. Mm-hmm. This can't be like a real problem. What the heck? Am I just meant to like sit here and stare at different slides until one of them looks like a tree? Like, you know what? If we knew what the tree was supposed to look like, then we could solve this in a different way and like actually say, you know, find me answers when the output would look like a tree. We could kind of write our rules in a different way. But I have no idea what look like a tree is supposed to mean. So I think it's something that we'll know it when we see it. Well, that's different. Are things coming together? No. Am I supposed to just sit here all day and wait for something to be a tree? Okay, we'll keep going for a little bit, and if this doesn't give us anything meaningful, you know, soon, then I'll sit here and despair. You know, like we'll think about our life choices and stuff. You know, it's like watching paint dry. You know, waiting for my tree to show up. Oh, that's something. It did say a tree, right? Yeah. I didn't expect it to take this long. So I think this is like the first one that we've done where there wasn't like an example like, well, you know, you should see a tree if you take the example input and do it like, I don't know, 100 times, you know. So I think my input or my code is correct, but I have no example to verify it against, unfortunately. So yeah, it's no tree, is it? I'm not being dumb, am I? Is that supposed to look like a tree, but I messed up my output? Whoa. Was that a tree? No, that's no tree. What the heck? I thought it'd be like really obvious, you know, like the whole thing is like a tree. It said they all arrange themselves into a tree, right? Isn't that what they said? So I think I'll keep iterating for a bit, you know, like I'll feel really dumb if like the answer's like right around the corner and I don't get it, you know. And if not, then we'll start trying to think of something else, you know. Yeah, I had certain things that looked like they could be a tree, so. Looked like it could be a tree. I mean, if I messed up some of my code somewhere. Someone says 2 hours later. Yeah. Is it really gonna take 2 hours to loop through? Does anyone have like a? Give me a hint. What kind of numbers are we looking at? Am I gonna have to sit through 10,000 of these to find it? In which case, I'll start trying to think of something else. You know. You know what? I thought this was gonna be like an easy part too. You know. It sounded pretty simple, and I'm like in my head, this is what I was planning on doing, just like writing something that would let me iterate through all the trees. But You know, okay. I'm going to keep hitting this button while I think of something else, you know, because if it really is going to take the rest of my life, you know, I'm not going to sit here for like 2 hours. And what can we say? What would we know about a tree? Like, what kind of properties would we think a tree might have? Like, I don't know, like a trunk or something? You know, a bunch of things in a row and in like a line. If we could like narrow our search space, you know, if I could think of like a rule like that, then I could say, find me a tree or show me values of n where the picture has something like a line in it, you know, of however long, or like, I don't know. And then, you know, maybe we find a tree a little bit faster. Man, okay, maybe I wonder if I'm doing something wrong, you know, because we keep coming across this image. And I don't have anything here to like see if we're like looping or whatever, you know, like I feel like we saw something that looked a lot like that before, although maybe I'm just like imagining stuff, you know. I mean, the input, I think my code's is doing the right thing though, so. Okay, I know I said I was gonna quit by this point, but like. Okay. All right, fine. You guys have won. Think of something else. Okay. Let's think about what a tree might look like. You know, I guess it probably has a point in like the very middle of the top. We could probably write something in there to say it's only a tree if it has like a point in the middle of the top, and then like one like on either side on the next row, and like that. I don't know. But since I have no idea what the trees are supposed to look like, you know, for all I know, they're skipping the first row or putting like a little border around it. I could just have this spit out like a bunch of stuff and write it to like files, and then I'll just like, I could quickly scroll through them all, you know. Sitting here pressing the buttons like pretty slow, right? But if I just had it dump out a bunch of crap, you know, I could just scroll through them pretty quickly, maybe. Yeah. Let's try to think here. Would a tree have a trunk? Would that mean it would have like a line of things? Yeah, but that rule would be a little bit tricky to write. You know, we'd have to say, given the robots, there are like some n number of robots. Like, let's say if there's like a trunk like here. I mean, we don't know how big a trunk would be, but we could say like there's a robot that has an X position. What was this? Maybe it says like 110. You know, Y of 110. And it has this X, and there's some other robot that has like 111 with the same X. You know what? Let's try that. But we'll start. Starting at the bottom, a bad idea. Because what if there's like a border around the image? Man. Okay. Yeah. Let's try sticking some more rules in here. Move robots. So, okay, this is gonna make my code super duper slow, probably. But it's okay. If we decide this is a stupid approach, we could just pick up where we left off at, 415. I'll just change my range for in to be 415 to 1,000 or something. So let's say there's a member. Robot move, robots, robot position. Okay, we'll call this robot A. Let's just see if we got like 3 robots that all have like the same X position, but like succeeding Y positions, okay? And this is gonna be really slow because it has to search for the whole list of like, I don't know, like 100 robots or however many stupid robots I have. you know, it's going to have to do that once, find a robot, and then search through the list again for another robot, and then search through it again, and then, you know, didn't find it, backtrack. This is going to be super slow. It'd probably be smart to, like, convert this list of robots to a tree at this point or something. But let's even see if we could even just do something like this. So we want 3 different robots. So robot is not equal to robot A. It's not equal to robot B. Okay, so find me a robot. Find me another robot that's different from that robot. And, you know, find me a different robot still. I could probably do, there's probably some other way to do this. Like find me a, like, not permutate combinations of 3 from this list. But we'll worry about that later. We'll even see if this is even possible. And we'll say robot position for maybe we should try the triangle. Should we try triangles? Nah. Or a line. Which one is more likely to be in a tree? Like a tip of a tree? Or, well, I guess, okay. There's no universe in which you print a Christmas tree and it, like, doesn't have a point, right? Unless there's a star on top of the tree. Let's assume there's no star and it's just like a triangle. I'm trying to think, is that a bad assumption? Okay. Do we want to try, let's do a line for now and see if we could even make this work, or if it's going to be like so slow it's impossible. Robot position for robot A is, we'll call it, for some X, and we all want to have different Y's, so we'll call it X and YA. So these all have to have the same X, okay? So it's going to find a robot A, it's going to find a robot B, it's going to get all the way down here, and then say, do they have the same X? Nope, it's going to backtrack. So actually we could find B, I guess, before we even worry about C. Okay, and then we'll find C, and then if it backtracks, you know, it doesn't have to re-find A or B again, you know. So let's say C, does it have the same X as the other 2 friends? No, it doesn't. Backtrack, find one, and we'll kind of iterate through the list till we find one that all have the same X, but then, you know, they'll have different Y's, and we'll say, let's say YB is like YA plus 1, and then we'll say, yep, and YC B plus 1. Okay, so I mean, this should find us matches where like 3 are in a row, which is probably, hopefully I'm hoping something that'll be in the image, you know, like a tree might have a trunk or something. So let's try that out. Yep. So 2, are they like 3 in a row? Yeah, here's 3 in a row. Okay. 2. Uh-oh. Why are we succeeding multiple times? Oh. So, okay. So here's another, I guess there's other values of robot A, B, and C. So we don't, once this succeeds, we do not need it to like check that rule and give me more answers, because we don't care. Either has 3 in a row or it doesn't, you know. So we need to put a cut in here after this, but if we put that cut there, then it's not going to backtrack all the way for different values of n. So I think, what's the right way to do this? If I am not a Prolog expert, so I'm probably not doing this the best way to do this kind of stuff, but we're just going to take all this stuff and stick it in a different rule, and we'll do it like this. And we'll put a cut. So this succeeds, we do not need to backtrack, that's fine. Maybe picture. Okay, cool, let's try that out. Oops. 4 has 3 in a row. Clearly this is like not meaningful. At least we're like skipping a few every, are we skipping a few? Man, now it's like hella slow. Kind of slow, right? Do these all have 3 in a row? Okay. Jeez. Okay. Here we go. Did we finally skip something? 20, no. 24, 25. Well, this, yeah, okay. Well, at least we've like narrowed the search space a little bit, you know, so at least every time I hit this button, I'm not like staring, I'm just doing one by one, right? So, what if we add like, man, does a trunk have like, could we assume the trunk is like 4 in a row? Is that a crazy assumption? I mean, we could like assume until we're like blue in the face, you know, and then if it turns out my assumptions were wrong, or I'm like going about this the wrong way, then I just like wasted like a ton of time. But I can't think of anything else to do besides maybe just like dump everything to like a file and scroll through the file till I see like a tree, which I guess would be like a little bit faster than hitting semicolon like 100 times. Yeah, okay. Maybe we should just do that, okay? It's not the worst idea I've ever had. We'll come back to this later. And we could start at like 400, I think, because we already know, what did we say, like 415 or something? So how do we print to a file? I think, let me look at my notes. I don't know how to print to a file. I gotta open a stream to a file. So I'll do, okay. Let's see, open. Oh, could I just do, yeah, stream, open a stream, right, stream, and then I'll do like print robots in, and we'll do like find all or something to make it like find all the answers. Okay, so we'll do find all in, then I don't care what the results are though, so then we could close our stream. Right. Yeah, I think I should do it, but now we'll just print robots. We gotta tell it to print to the stream and not just to the REPL. So print robots in, take the stream. We'll pass that along. And I think the other thing is we probably want to print in, otherwise, you know, I'll have all my Christmas trees and then I'll not know if I have it, you know, I won't know which one is the right answer because I didn't print in like a clown. So let's do, but this has to write to stream. I think that's the to arity. A right line takes a stream and a term. Yeah, cool. And moves. But we don't want to do it there. We want to do it after we have a concrete value for end moves. Let's write like a blank line before that to like visually separate them a little bit. Okay, print robots. Print one robot, to stream, blah, blah, blah. And I think right also has a to arity that takes a stream. Is that right? Yeah. Okay. But new line also gotta give it the one arity. Yeah, okay. Let's try this out. I'm gonna say, I guess actually we should probably be passing or setting this constraint outside of this function, right? So let's say, can we do that? Can we say, oh, final in. Yeah. Wait a second, print robots. Yeah, okay. And let's just try like 400 to 402. Why is it? It's being really slow right now. Oops. I meant to type period. Doesn't know print robots is right here. Okay, make sure I load my code. What's our complaint? Print robot doesn't know about not compiling or something. Print robot. Blah, 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 blah. Print robot needs string. There we go. Mm-hmm. Okay. What am I doing wrong? String. Right, string. Okay. Am I on drugs? It's like literally right there, right? Okay. Sometimes this trips itself up. I'm gonna restart it. Yeah, let's do this. And is in, let's say 400 to like 402. Yeah, boom. What? Okay. What? There are definitions for it. You can't be serious. Like, it's right there, right? I'm out. Print robots. There's the 3 arities right there. Print robot. Okay. It says this doesn't exist, but it's like literally right there, right? You know, so. Am I drugs? What have I done? What the heck have I done? Dude, it's like right there, right? Okay. Okay. I'm loading the file. It's not complaining about anything, okay? I'm saying print those freaking robots. Oh my god. Okay, so now we should have out.txt, and yeah, okay. I don't know what I did differently that time, and now it works. You know, sometimes it's just like kooky, you know, when you're loading stuff. It makes you question your sanity. So let's try that again. But we'll do like, I don't know, like 10,000 with like actual. Okay. I wonder if we could kind of watch it as it writes, or if it's yeah, okay. Maybe we can. Yeah, you can see it getting a little bit bigger. Okay, and now I guess we just... Man, if I was smart, I would have put like some kind of like separator between them so I could just like jump to each like occurrence of that separator. Maybe I will do that. Okay, cancel. And we'll say a new line. We write the number of moves, and then we'll write like okay, let's try that. Oh, you know what? Things are in a totally messed up state now. Now let's do it. Let's try this one more time. Fly makes printing out 013, not sure what that is. Me either, honestly. Where the heck is... It's not loaded. It didn't load up my new version of things. Okay, okay. New plan. Forget this. We're just gonna restart Sweet Prolog. Let's see. Yep. Okay. Sweet Prolog. Okay. Now don't try to mess with me. Okay, there we go. Now, and so these should each be separated now. Yeah, okay. And one of these has to look like a tree, right? Yeah, this is a little bit quicker, I guess, to iterate this way than it is to like watch and watch them print one by one. Oh, but now we're kind of iterating faster than it could print them, huh? Whoa. Oh, well, that almost looks like something. Man, I got so excited for a second. Oh, we've paste. Where the heck is everything else, huh? There we go. I keep seeing this one. You know what? Man, I wonder if my printing code's like messed up or something. Because I feel like I keep seeing things that look like this. And I feel like who would write a problem where the expectation is that you just loop through 6,000 pictures until you see one that looks like a tree, right? You know, I would have thought I would have got it by now. So, if I haven't, then, you know, maybe that means I'm doing something wrong. But I don't have any kind of input to, or example input to validate my code against, you know, so. Who the heck wants to like jump through like 800 trees? Okay, this is my this is my new least favorite problem of this year so far, because it's just like, you know, you either got the example or you didn't, or you know, if you got a number and then you could put it in and check, right, and you just run your code, spits out a number, it's the right answer, it's the wrong answer, right? But this is like, I can't just like have it spit out an answer, right? All right, this is preposterous, right? I'm not gonna sit here and watch flip through 9,000 trees. Okay, so, you know, if the answer is like 5,000 or something, I'm not gonna sit here for like 2 hours and wait to get it, right? So we gotta start thinking about something else. So I guess there's two possibilities here, and one of them is that my code to print out the trees is like totally busted, and I already had a tree and I just didn't know it when I saw it. Which is like totally a real possibility. Especially, I'm thinking, because I kept seeing those things that looked like, you know, something. Maybe I'm just hallucinating, but it looked like it was trying like this, right? Man, that's Christmas, right? Is that, if that doesn't look like Christmas, I don't know what is, right? So, am I printing things wrong? Is that like is that supposed to be a tree? And I just printed it wrong, or am I really? Do they really expect me to just like sit here and iterate through? You know, 5 billion different pictures until I find one. What are we gonna do? Man, well, I'm sad now. I don't know what to do. I tried my stupid rule to like look for things that had like lines, and because I could make that rule more complicated and fancy, and look for like a really long line or something, or look for a triangle or a point. But I spent all this time writing this rule, and my code would be kind of slow, and then it doesn't even guarantee I'd find the tree anyway, right? All right, I think at this point I'm gonna call it, and then I'm gonna sit and reflect on my life choices, and maybe come back to this like with a fresh mind later. So thanks everyone for joining. This is the first one I haven't got yet. So we'll come back to it. See you later, everyone. Like and subscribe below.